Hey, good afternoon, everyone. I hope you are doing all right and ready to learn some physics. Okay. So we started first, like defining charges, and then of course we defined field, and then we talked about electric field lines and so on. So those were new things we learned in the semester, but at the same time, we also learned how to, let's say, solve problem related to charged particle moving in electric field, just like a mass moving in gravitational field, right? So kind of similar idea. And we said, okay, we can use acceleration. We can find acceleration of such charged particles. And that is force over mass means Q times E over M, because force on charged particle in an electric field is Q times E. So that's what we learned. And then after that, we said, okay, if the field is uniform, that means constant. When this is constant, then A gonna be constant, just like we have a gravitational field, right? Gravitational field, what's the acceleration at that time case? Constant. Similar idea, okay? So once we have that, we can use kinematic equation. So by doing this, we use dynamics or laws of motion, right? And this is kinematics. Kinematics, dynamics, and what did we learn in physics 1 after that? So we learned three main things in physics 1: kinematics, dynamics, and conservation principles. So conservation of momentum, conservation of energy, okay? And I said, okay, we're going to be using that in physics 1. And if you decide to take physics 2, we'll be doing the same thing. And that's what I'm doing here now, okay? So dynamics, oops, kinematics, right? And today we're going to start, we'll talk about energy and how to use conservation of energy in electric system, okay, electrical system, or for charged particle moving in electric potential. So that's what we're going to be doing. But we did not quite finish last class's slides. So I have these, leftover slides from last class, 2 or 3 slides. So the first one being this, which is very, directly related to the problem we did towards the end of last class. So I'm going to open the poll, and you have a minute and 30 seconds to poll on this. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Okay, let's see what we got here. So mostly B, but there are A and C competing. Nobody said they had no idea. Okay. At least you know something, right? That's good. Okay. So think about, so we have, let's say, big Earth here and Earth gravitational field coming down like that. And when we throw a mass horizontally like this, what happens? It hits the Earth, right? Eventually. If we just let it go, it's going to just directly come down. But if we throw, so that's projectile, right? What happens? It comes like this. So in gravitational field, what happens is mass, these masses, they are always attracted. But in case of charges, they may be attractive or repulsive. So we have to pay a little bit attention on that, okay? So for that, what we need to pay attention is that, for example, let's say if I have electric field going something like this, what that means positive charge is there, negative charge is there somewhere, okay? That's what causing the field. So field line originate at positive and terminate at negative charge, right? So that we learned last class. We just talked about that. So that's that. So that means this field is something like this, okay? Here the field lines are going up, so that means positive charge must be something like that, and negative charge somewhere there, okay? So you don't need that, but if you like, you can put charges like that. So if I release, so for example, if I have a positive charge here, and I have a negative charge, and if I release an electron, so this electron being negative charge, it gets pushed by that and pulled by this. So that means it's going to move towards this positive charge, right? Negative charge gets attracted towards the positive charge. So that is like saying, okay, unlike charges attract. So in terms of field line, what? Then we need to remember negative charge moves opposite direction. Opposite direction to the field E, because by definition, field is the path a positive charge would follow, okay, when it is free to do so. So just like I said, if I let negative charge go here, the negative charge, if it wasn't moving, it would just go towards the positive charge. But just like when we throw a rock, what happens? When a moving electron enters something like that, So it does not just go directly towards positive charge, rather it gradually goes like that, okay? So if it was positive charge, if this was positive charge, then that would be correct, okay? But this question is about electron means negative charge, so that's why this is the correct answer. So negative charge moves opposite direction to the field. So keep that in mind. If you have to understand, draw this, and you can see and recall that opposite charges attract. Okay, so these things you need to build those knowledge on. So that's why there are so many questions, something like this, like how the charge is going to move, and so on in the practice and pre-class, and of course the note I have posted. Okay, so certain thing you need to keep in your head. Okay, so anything you'd like to add or ask on this one here? Okay, then let's move on. So, how does the field line interact with conductors, especially the conductor that has, positive and negative charges, of course, and they are in equilibrium, unless we are putting that in electric field, okay? It is in equilibrium. So, in that case, what happens is these field lines just land perpendicular to the surface, makes 90-degree, okay, when they hit the conducting surface where charges are not moving. If they were not, let's say, landing 90-degree, rather at some incline, that means there would be net force. That means charge would be moving. So this conductor wouldn't be at equilibrium. So if charges are not already moving, and that's the case for, let's say conductors, there are positive, negative charges, and they are spread all over the, surface. So when field line, let's say, arrive close to that, then what happens? So this being negative charge here, field line is entering towards the negative charge, of course. If this was positive charge, then field line would be leaving the surface. When they do, they would be perpendicular, okay? So here you can see the same thing here. So on the negative side, they are entering, and positive side, they are leaving, and they are 90-degree, okay? Look at here, positive charge leaving, and it's leaving 90-degree, okay? So field lines are always perpendicular to the conductor, okay? So keep that in mind. And let's say if we have conductors something like this, and if we apply field lines, what happens is there's going to be this kind of polarization of charge, okay, separation of charge, because negative charge wants to move away from the opposite direction to the electric field, so they're going to line up here. They cannot just skip from the conductor. It's like they are trapped inside a room, right? They cannot crash, let's say crack open the wall. So they're going to line up on the wall like this, leaving the positive charge behind. So when we have that, what happens is now there is new field because of this separation of charge. Remember, field line always, this new field line, any field line, they always goes, they go from positive charge to negative charge, right? So what happens is going to be in the opposite direction to the original or the external field. So there's going to be some cancellation here inside. So because of that, what happens inside a conductor field is 0. Okay. And when you have pointed structure like this, there are going to be a lot of charges there. And because of that, what happens? Electric field going to be larger because electric field is charge density, surface charge density divided by this permittivity of free space, electric permittivity of free space. So what happens because of that, you see there are a lot of these field lines coming out, but they are kind of fanning. Why? Because the one that's coming out wants to be perpendicular here. The one that's coming out wants to be perpendicular there. So there are, all of these are perpendicular to the point, perpendicular to the surface uh, at the point where they are coming out. So that means we can think of this as like having horizontal components and vertical components. So all these vertical components add up, but the horizontal component corresponding, they cancel, okay? And the vertical component adds, okay? And that's the result. So you have this large electric field near the tip of this pointed metal, okay? So because of that, what happens is they can discharge the charges from the environment. So for example, if negative charges, for example, appear there, they're gonna just get inside or they're gonna be neutralized by this field. So that's why you see this lightning rod, they are pointed and they are put in the roof to protect, okay? So these kind of properties of the field lines in the conductor, and that also helps to design what's called Faraday's cage. Okay, so over here, what happens if this person was standing there? Jack would be on the ground, electrocuted instantly. Okay, but because this person is inside the cage, what happens is, see, from the pointed structure, a lot of field coming there. And what happens is it ionizes the air. So in that process, it's emitting light. So these charges are flying, okay? And when they hit this conductor, what happens is they just stay outside, electric field inside this hollow thingy, 0 we learn. So that means this charge is just gonna go to the ground. The person is not affected by that lightning. It's like lightning strike, right? Okay, so that is the electric field and its interaction with the conductor. Okay, so now we're going to move to another chapter called electric potential. So far we had electric field or force or field, right? They are kind of equivalent thingy. So we can talk in terms of force or in terms of field. So now we're going to move to potential, like a potential energy. Okay, so it is like a potential energy. Just like we had a gravitational potential energy, elastic potential energy in physics 1, now we can have electric potential energy. And those kind of potential energy comes in handy. For example, they are translated in this kind of electric devices that can measure the rhythm of our body, right? So here you see the unit you see here is that V means volt, okay? So that means it is measuring the potential, electric potential. So unit of electric potential is volt. So it looks like this is healthy display. See, it's a regular, right? But if it becomes irregular, that means there is some problem. Okay? So anyway, so let's talk about electric potential. So potential, before we talk about potential, let's talk about energy. So we learn about the gravitational potential energy, right? And we said, okay, gravitational potential energy is written by mg, this force, times y, or the displacement, mgy, mgh, mgd, something like that. So this equation is like this, assuming that at the ground, the potential is zero. Potential energy is zero. Okay. So work done transfers the energy. So what is the potential energy then? Work done by field or force related to that field. So gravitational force, when gravitational force does the work, what happens? We say, okay, that energy gets transferred to the object, and the object gonna have either higher or lower gravitational potential energy. So for example, when something is coming down, its gravitational potential energy is decreasing. When it goes higher, height increases, means gravitational potential energy is increasing. So we can build a similar idea for the electric potential energy as well. So for example, think about a charge, source charge as Earth. It's going to either attract, Earth attracts, always attracts, but the charge sometimes attracts, sometimes repel, depending on what charge it's looking at, right? So when it's attractive, so for example, when this charge is positive here and the source charge is negative, so there's going to be this electric force, right, between these two charges, just like gravitational force between this mass and, of course, the Earth. Okay? So similar idea. Okay? Nothing new. Only that this field is now created by charge, not by mass. Okay? Only that's the difference. Otherwise, it's the same idea. Okay? So now, what happens? If a charge is moving from, let's say, very far and arriving over here, that means this is doing work. But if we are making it, if we just let it go, what happens? It's going to accelerate because there's going to be net force. So if we want this to bring orderly, just like we bring a book down by holding it, so that means we are applying force upward, right? When we do that, what happens is we are applying force, and this force is there, so this is like external force, and this force is the electric force, right? So now what happens is the work done by this is transfers, gets transferred as electric potential energy. Okay, so work done by this force is transferred as electric potential energy, and we learned that work done can be written as a product of force, displacement, and cosine of angle between them. Okay, so this theta is not any angle. And we also learned that change in potential energy is equal to work done by external force, this force, or negative of that field. Okay, so work done by this and work done by that, they're going to be equal in value but opposite in sign, and that's what that is. So if you want to write change in potential energy, it's going to be equal to work done by either the external force. For example, here the work done by external force, like we are lifting a book, so we are doing work, whatever. So what we are doing is we are transferring some of our energy to that book So because of that, as height increases, its gravitational potential energy rises. Same thing goes with this electric potential energy as well. So if we look at work done by this, that would be positive because theta between R and F is 0 degree. So anyway, so they are kind of opposite, change in potential energy and work done. They have opposite sign that we learn in physics 1 as well when we talked about gravitational potential energy. If you did not learn, then learn it now, okay? So work done by external force and change in potential energy, they have same sign, but work done by the force of the field, like work done by electric force, work done by gravitational force, that work done and change in gravitational potential energy, they're going to have negative sign. So what happening is it's lowering the potential energy. So that's why that's negative, okay? And now what we can do is, in that case, in particular case, let's say angle is 180 degree. So in that case, this is -1 and this negative, both negative and negative makes it positive. So electric potential energy can be written as a product of simply F times R. And we know this is electric force, KQQ over R squared, Coulomb's law, right? And this R. So one of the R cancels, giving us this. Okay. So this is the equation of electric potential energy between two charges. So it is like a work transferred when bringing this charge from very far to that point. Sometimes you may also see written from infinite distance to that point. Okay. So this is the separation distance between these two charges. That's how it works out, okay? So this is the electric potential energy equation. So that's the formula. So it's like saying, okay, gravitational potential energy is mgy, that's what we used. So that is something like this. Remember, this mg can also be written as g m1 m2 over r squared. So if we were to use that one over there and cancel this y by one of the r, then you have exactly same equation. G, some constant, times product of two masses over r. Same thing here, constant times product of two charges divided by r. The same equation basically, okay? One is the result of masses, another one is the result of interaction of charges. That's only the difference. Otherwise, it's the same thing. Okay, folks? So that is the electric potential energy. So now, what happens? Electric potential energy can be positive or negative, just like gravitational potential energy is. So we don't need to worry too much about it. If we plug in the sign of these two, then that's going to give you the correct sign of the potential energy. So for example, in this case, what happens is this one is positive, let's say Q is positive, and this Q is negative. So one positive, another negative. That means electric potential energy is going to be negative, just like we saw over there. Okay. But if this was negative as well, if this charge was also negative, then this Q negative and this Q negative means double negative, product of double negative becomes positive, right? So that's how we can determine the sign of potential energy. Where does the sign of potential energy comes from? It comes from sign of charges. Remember, when we are writing force, force is a vector quantity. So because of that, when we use this formula, we did not use the sign of the charges. Rather, if I have a positive and negative sign, I said, okay, they're going to be attractive forces, and we drew arrow. But energy is a scalar quantity, so smaller negative number is larger than bigger negative number. What do I mean? So for example, negative 10 joule is smaller than negative, let's say 1 joule. Okay? Why? Because this is more negative, means smaller. That's what we say. It's just like saying our bank account has, like, let's say you have a checking account and then credit card from the same bank. Credit checking account has $100, but credit card balance is 1,000, let's say. Okay, so you are in 900 debt. So that is negative balance. Okay, and negative 2,000 is worse than negative 1,000, right? Your debt, 2,000 debt is worse than 1,000 debt. Anyway, so same idea here. So charge come, sign of the potential energy comes from the sign of the charges. So we plug in the number with the sign while calculating energy. That is different from how we calculated the force, okay? While calculating forces, we only put the value of the charge. We did not worry about the positive and negative sign. By using positive and negative sign, we drew the separate diagram, okay, to figure out the direction of force. But potential energy does not have direction. It has only value, and the value can be positive or negative. So if you see positive or negative sign in front of energy, that is part of that value. But when you see positive or negative sign in front of force or field, that means that negative sign simply means direction. Okay, so that is one main difference handling scalar quantity and vector quantity. Good thing about scalar quantity, we don't have to draw triangles and add that vector really, right? Unlike the case of force being vector, field being vector. Okay. So now with that, I have a question for you. So what do you think? So think about what force is doing work. So the angle has to be between that force that's doing work and displacement, okay? So read question carefully. So this charge is slowly being moved up, let's say, by pushing by external force. Here I am just saying, okay, this line or little wire is pushing it up. Why? Because it's moving towards the positive, right? We are making it move towards the positive sign, otherwise it wouldn't move. So that's why we have to apply external force. So here is talking about net work done. Means you need to find work done by all possible forces acting on it. Let's do 30 more seconds. Oh, turns out my microphone is very far today. Okay, 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So here in this case, there is this field in that direction means the force is in that direction, electric force, Q times E. And this is external force, right? And it is moving with constant speed. So when it's moving with constant speed, net force is going to be 0. Net force 0 means work done by net force also going to be 0. Okay. So one is doing positive work. The external force here, maybe I should write external to not to confuse with the electric, right? Push force. Let's say force applied. Okay, applied force is good. So here displacement is in that direction. Applied force is in that direction. So theta is 0. So work done is F applied times D, force times displacement, right? Force times displacement times cosine of angle between them. So in this case, it is 0 degree. Cosine 0 degree is positive 1. So it's doing work Fa times D when it is lifted by a distance D, for example. Now, work done by, that was the applied force. Now, work done by electric force, for example. How do we find that? Electric force times displacement times cosine of angle between them. So in this case, electric force is down and displacement is up. So the angle between them is 180 degree. So that's why it has to be 180 degree, and it becomes negative Fe times D, because cosine 180 degree is negative 1. So this is positive, this is negative, and since this is moving with constant speed, both forces must be equal. So that means when we add these two, we're going to get 0. So here we learn how to find work done by external force, how to find work done by electric force, and how to add them together to get net force. I mean net work done, okay? Or you can say, okay, net force is 0 because it's moving with constant speed. It's not accelerating, means the acceleration 0 means force is constant, okay? And that means force is 0, I should say, net force is 0. So force itself 0 means it's not doing work, 0 work. So two different ways of looking at it. So if you recall one of the worksheet from physics 1 in the work and energy thingy, I had you, let's say calculate work done by several forces and then add them together, okay? And so on. So that's the technique we are using here. Okay, so that means correct answer would be, in this case, what? So different from most of you thought, okay? So in this case, it's 0. So positive and negative, they were like equal. So if the question was work done by this push force, applied force, that would have been positive. Work done by electric force would be negative. But in this case, it asks for net work done. So that means you need to add both of them. And since one is positive, another one is negative, and forces are same, displacement same, means the total becomes 0. Okay? Okay, anything you like to add or ask? Okay, then let's move on. And I have more question for you. Looks like let's forget about that for a moment. Okay. So I'm opening the poll and you have a minute to answer this question. So you see there is positive charge, there is negative charge. Okay. So I'm asking you, what's the direction of field in this case? These things you need to keep in your head. So I'm bringing that question here again for the repeat. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. So towards negative charge, that is correct. Okay. We learned that field starts at positive and end at the negative. Okay. And so that's why B is correct answer in this case. Now, what is the direction of force on a negative charge here? So for example, let's say if I were to bring negative charge here, what would be the direction of force? Okay. So I'm opening the poll and you have only 30 seconds to answer. Okay. And choices are given here. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. So mostly A. So negative charge gets attracted by positive charge. So unlike charge attract, like charge repel. So that's why B is not the correct answer, but A is. So now direction of force here on the negative charge is in that direction. Okay. So now what is the work done? So to find work done, what do we do? Again, we just like we did before, we need to do force times displacement times cosine of angle between them, right? Force and displacement. Here, there is just electric force. There is no external force. So that means the force is in that direction, means it's moving in that direction. Okay. So that means the angle between them is 0 degree, means this cosine 0 degree here becomes positive 1, means work done is equal to force times displacement, and is positive. Now, how much is force? Force on a charge in terms of electric field is given something like this. So this or that. Okay. In terms of field, this. In terms of force, that. So what is the change in electric potential energy? Change in electric potential is what, right? We know change in electric potential energy is equal to, change in electric potential energy is equal to negative of work done by that electric force. So in this case, work done is positive. So that means there's going to be negative sign and the work done is this. It's going to be there. It's going to be that. So that's how we find work done and its sign. Okay, now your turn. There are quite a few. So agent or external force or applied force, okay? So it's like saying applied. And field force, and this is net force, okay? So situation is shown something like this. So there is positive charge. So this charge is moving with constant velocity here. So here it's just the sign, not the values. So which choice matches the correct combination of these? Work done by this, that, and the net force, okay? Okay, so you have 2 minutes. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got. So it's kind of a bit shifted towards C and D. That is good because net force here is 0 because it's moving with constant velocity. So work done must be this, not that one. So easy to eliminate those two. So now agent. So electric force is acting in that direction on the positive charge. See, it's moving in that direction. So that means applied force must be in that direction. So applied force and displacement. So displacement is in that direction. So the theta between applied force and displacement, that is 180 degree. That makes negative work by that, okay? And the force itself in this case on the positive charge force is acting this way in the direction of displacement. Okay. So that means theta is 0 in that case. Okay. So displacement here, applied force here, and electric force and displacement, they are in same direction. So theta is 0. So work done is positive. Here, work done by applied force is negative. Okay. So looks like C is correct answer in this case. So we need to systematically use the formula by drawing FD diagram, not free body diagram, but FD diagram. If you took physics 1 with me, probably you are familiar with FD diagram. And that's what I'm doing here. Why do we draw FD diagram? To figure out the angle correctly. It's the angle that determines whether it's a positive or negative work. Okay. So it is opposite of what we had before, because in the previous case we had a negative charge. In negative charge and positive charge, it's going to be opposite, right? But you will never miss if you use this. And of course, the formula for work done is FD cosine theta. You need to determine theta properly. So now let's suppose we have two charges, given two charges, and we want to find the work done. Sorry, not the work done, potential energy. So the two charges and distance given means we can use this formula. Oh, potential does not have R square, by the way. Okay, so there looks like there is a question on the Zoom. How do we know applied force is on the left? So see, it's like electric field force is like a gravitational force. It's pulling down, let's say, pulling towards the negative here plate to the positive charge, right? So it's going to accelerate if we don't apply force in the opposite direction. It's moving with constant velocity, means the other force must be applied upward so that it moves with constant velocity. So if you want to make something go with constant velocity on the Earth's field, you are applying force upward here. Weight or the force from gravity is acting down, so you are applying force up. So that whether it's moving up or down, as long as it is moving with constant velocity, these two forces are balanced. Same idea here as well. Okay, that's a good point. Did not say which way is the force, right? So now, coming back to this problem here, so there is one charge, there is another charge, separation distance between them is R. So all these informations are given, okay? K is constant, we know, Coulomb constant. Oh, someone is writing on my slide. Ten to the power 9. Newton meter square, and this time is a Coulomb, so Coulomb is squared, okay? So that's a K, and Q is 2 Coulomb. Okay, it's given in Coulomb. If it was micro Coulomb, and often you may see charge given in micro Coulomb, and that means you have to go like 10 to the power negative 6 Coulomb, okay? But this time here, it's a Coulomb, so we can just leave like that. And this is 1 Coulomb. Both of these are positive. There is no negative sign. And R is 9 centimeter. We need to convert that to the meters. So 9 and centimeter. So there are 100 centimeter in 1 meter. So centimeter cancels, giving us 0.09 meters. Okay. So all these numbers are known. So it's just a matter of plugging them in and finding the value, and it's going to be positive because both charges are positive, means the potential energy also going to be positive. So to bring this charge from very far to this point, external force had to do work, and that energy was stored here. This charge says, okay, I'm not going to go there. I'm not going to go there because there is positive charge, right? So it gets repelled. So if you want to bring it here, you are pushing it here with this force, and you did the work while bringing this charge at that point. Otherwise, it wouldn't stay there. Okay. So that's why this becomes, it has now positive potential energy. That's another way to look at it. But just looking at the sign of charge and looking at this equation gives the same thing. Okay. So that's what that is. Okay. So this is R, not R squared. So field and force, they have R squared, but potential and potential energy, they have just R. Okay. Okay, so now here is another question. So we are looking at change in potential energy. So particle is moving which way? This is positive charge. Probably you can tell which way it moves. Okay. Oh, it tells you actually it's moving this way. Okay. Even if it did not tell, we can tell it would move that way because it's getting pushed by that positive charge. Okay. So what do you think? 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. So it is positive charge, and this is also positive charge. Basically, what's going to happen here is that force is acting this way, right? Electric force, and displacement is also in that direction. So theta is 0. So work done going to be FED cosine 0 degree. So work done is positive FED. But we know work done and change in potential energy has negative sign in between. So relationship is that, okay? So that's why it's going to be negative. So that's why the answer is negative in this case. There is other way you can do it. So for example, let's use this formula of potential energy, right? So UI here, what is that? That is K, and this charge is E positive, and this is some positive charge. Let's say that is Q, okay? And let's say this distance also is not given. We can say, okay, that is R1, okay? So this number is positive, agree? K is positive, E is positive, the sign is positive. Sign of both charges positive means this is going to be positive. The question is not about UI. Question is about finding change, okay? So to find that, we need UF as well. And again, it's going to be positive. K E Q over, let's say, R2 squared. Let's say that distance of this point from this source here is R2. So this is another way to look at it, okay? So now what happens here? This is also positive. This was also positive. So now when we find change using this formula here, so let me get rid of these. So when we do that, what happens? We need to write this one first. KEQ over R2 squared minus KEQ, right? Over, oh, not squared, my bad. They're not supposed to be square there. Okay, so R2 and there is R1. See that? So now you can tell which number is bigger here. E is same, Q is same, K is same. So maybe we can just factor this out to see it clearly. Oh, one is R1. Why am I keep writing R2 for both? Okay, so one is R1, another one is R2. So in this case, R2, since R2 is bigger than R1 because see the final point is of A, right? R2 is bigger than R1. What happens? That means 1 over R2 is smaller than 1 over R1. So it flips, right? So for example, let's say if this is, let's say, how much? Let's say 0.5, okay? And the R1 is, oh, R1 is 0.5, let's say. R1, let's say, is 0.5. We don't need number. You can tell without number, but just in case. So what happens here? This is 1 over 1, and this is 1 over half, means this is 2. So when you have denominator, you are dividing by smaller number, result going to be larger, right? So it's like subtracting, 1 and minus 2. So that means it's going to be negative, okay? So difference going to be negative here because you are subtracting larger number. Why this number, second term, this one is larger? Because it is closer. When it is closer to the charge, what happens? Potential is more. Potential energy and distance, they are inversely related. See, R is in the inverse of that U equation, right? So larger the distance, is smaller the value. So that's why this one is smaller than this one means difference going to be negative. And that's how we do it. Or you can just look at work done and recall work done is just equal to change in, so negative of change in potential energy, or change in potential energy is negative of work done by the field force. Okay, so that is that. Okay, oh, it's 3:07. So let's take break for 5 minutes. Okay, and I'll see you in 5 minutes. Okay, folks, welcome back. So now let's suppose if we have more than two charges, how do we calculate potential energy, okay, of the configuration of charges? So basically it is, straightforward. Just you write formula and you get the answer. So potential energy, we learned that when we bring charge, from very far. So when they are very far, there is no force acting on them. So they can move freely. But if we want to bring them closer, then something has to do work to bring them closer, right? So in that process, if I'm bringing one charge near another charge, I am doing work. That means whatever work I am doing, that goes into the potential energy of that object, all right? So in this case, what happens is this negative charge wants to come to the negative charge on its own. So I don't have to, I'm not doing work pushing this way, rather I am pulling this way, okay? So that means I'm not adding energy, rather I'm taking up some energy there, okay? So anyway, so that's what I'm writing here. We saw this figure, so it's just like saying, okay, there is a negative charge and there is positive charge. So if you want to bring this charge, let's say if you are bringing this from here, something like that, that means you are applying force that way, because this way is going to just move on its own because positive charge gets attracted by negative charge, right? And same thing goes with this one as well. So that's that. So looks like both of these gonna have kind of negative energy. So work done, uh, you can, that work done translates to the energy. So work done by electric field, but we don't need to worry too much about it. We can just remember this formula KQ Q over R. And we are using just that formula here. You see that? So here what we have is these three terms. Why? So this potential energy between two charges. So you can see here there is Q1 and Q2. We said this one is Q1 and this is Q2. So they're going to be potential energy between them. And they're going to be potential energy between them. And they're going to be potential energy between them as well. Okay. So this three combinations. So that's what you see. So there it appears like one pair, another pair, and then another pair, right? So those pairs, we are writing this equation. So here I just added here positive sign, and since all of them have k in them, I factored the k out, and since there are several r, so I'm putting subscript to denote them there, just like I did for the charges. Okay. So now, when you plug in the charges, make sure you keep track of this sign. This has a positive sign, this has a positive sign, but this one has a negative sign. So Q2 has a negative sign, means this is going to be negative, this is going to be negative. But Q1 and Q1 and Q3, see Q3 here, Q1 here, both of them are positive. So this term going to be positive. And couple of things we need to keep in mind. These are given in centimeters, so we need to convert that into meters. And the charges are given in microcoulomb. So for example, Q1 in this case would be 5.5 times 10 to the power negative 6 coulomb. Because let's see, 1 coulomb is 10 to the power 6 microcoulomb, or other way around, 1 microcoulomb is 10 to the power negative 6 coulomb. Okay. So we are going from micro to coulomb. So that's why we need that one there. Okay. And we need to do same for all of these. But this 10 to the power negative 6 is going to be same for all these terms. So we can factor that out. Two of them actually. Okay. We can factor, see, 10 to the power negative 6 from one of those, and Q2 also has that 10 to the power negative 6 coulomb, that conversion factor, right? Q3 also has that. So that means when we are multiplying this 10 to the power 6, two of these going to multiply. And that's going to happen to all of those. So if you like, you can write, see, the K is 9 times 10 to the power positive 9. And then now you can write 10 to the power negative 6 from one of the charge and 10 to the power negative 6 from another charge. So I'm factoring them out because all of them will have that one. So that way what happens is, now for example, all you need to multiply is 5.5 times negative 6.5. Q1, Q2 means that, right? And then R12 means 12 times 10 to the power negative 2, because we need to divide by 100. So rather than writing that one there, it's going to be in all of those terms. So you can, if you like, you can bring it here, or write everything in place and punch that in calculator without making mistake, right? Q3, 2.5, Q2, Q3, and distance between them is 16 times 10 to the power negative 2, but I already factored that negative 2 out here, so I can just write that. And there's going to be one more term. Looks like I'm running out of space here. So that would be Q1, Q3. So that is 5.5 times 2.5. Both of these are positive here. Oh, what's the distance between them? What's the distance between them? So they are in right triangle. So this is going to be square of 12 plus square of 16 under the square root. Do I know what is that? Maybe not. I'll just write like that. Okay. I use Pythagorean theorem here, because two side lengths are known in a right triangle, so I can find the hypotenuse. Hypotenuse square is equal to sum of the two side squares. So yes, this is long. You need to use calculator, and turns out you get very simple answer. So you will have negative sign because this term is negative, this term is negative. So more negative than the positive. So net becomes negative here. Okay, so I'll leave it there and gonna move on. So when we have a negative charge here, everywhere around it at equal distance, they're gonna be equal negative potential. We know that, right? If this was positive, let's say if this was positive, then this would be positive. And everywhere around this, it has the same potential, okay, at equal distance, because we know in the formula of the potential energy is KQ over R. So now, what is potential then? So this is not potential energy. We're talking about potential. So we have this potential energy. Divide potential energy by unit charge, just like to find field, you divided force by charge, right? Same thing here. To find potential, and we denote potential by uppercase V. And by the way, its unit is also volt. So notation is both unit and the quantity, both of them has this V here, okay? So what happens here? One Q gets canceled, leaving KQ over R. I think that's the simplest equation we have, okay? And that's what I'm doing here. So this is the formula for potential of, see, without this Q, that is the formula for potential energy. But once this Q, we divide by Q, one of the Q cancels, leaving us that. And this is what we call source charge. Okay? And that is what producing potential, just like, charge produces field, charge also produces potential. And there is a relationship between field and potential. We'll take a look at on that one next class. But it's like you can talk in terms of force, you can talk in terms of energy. Same idea here. We learn how to talk in terms of, force and field in the, last two classes. And here we are learning how to talk in terms of energy. And there is potential energy, and there is just simply potential energy per unit charge, okay? So if you know potential, then you can get potential energy just by multiplying by that charge. So what happens? There is potential everywhere around this source charge. If you bring a test charge over there, what's going to happen? Now there is potential energy between them. How much is the potential energy? Whatever potential is there times the charge itself, okay? So that's how you can think. Just like we had for the force, we had like force can also be written as a Q times E, right? Same idea. This is for potential and potential energy. This is for force and field, okay? So these things should be in your head, basically. So you should be reading so many times, doing so many things related to this, it should be in your head. Now, if we go from one point to another point, so for example, around here at RA radius, we have one potential. We say, okay, that is, let's say BA here. And potential over there is BB. So difference between these 2 points, potential difference, we call that, okay? And if we have to write in terms of, let's say, these values, what we can do is, okay, we can say KQ over RA, final minus initial, maybe we want to do RB, and then KQ over RA. That's going to be the potential difference. This is same as this one. So this is potential at point B, so we are calling that BB. And this is potential at point A, and we are calling that BA. Okay? So that's the potential difference. So unit of potential is volt. And we denote that by B. And the voltage, we say, okay, there is a 110 volt outlet, or our computer needs 12 volt, or a battery has 1 volt, 1.5 volt, one cell has a 1.5 volt, car battery 12 volts. So what are we talking about? potential difference. See the car battery, I don't know if you have ever looked at it. It has a positive and negative terminal. Even a dry cell. Do I have that cell here? Maybe or maybe not. Oh, right there. So the cell has a positive terminal and negative terminal, right? So the potential difference between these 2 points is 1.5 volt. So we say this battery is 1.5 volt battery. So what is that? That's the potential difference between these 2 points. Okay, so that's what that is. Potential at a point, and if we have 2 points, then it's going to be potential difference. It's like saying position here and then position over there. Difference in position is a displacement or height. Same idea, potential difference here. But these are not vectors, okay? So now here is a question related to potential and field, right? Remember, field is like a potential, but it has a r square in it, and it is a vector. And potential, so it's scalar. Did you notice any difference between these 2 formulas? It's easy to miss. One has r squared in the denominator, another one has just r. Okay. Okay, with that said, I'm going to open the poll and go ahead and poll. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So we have A and B competing. And there is also C and D. Okay. So field is a vector quantity. So here, when we find field at a point, we assume there is some tiny positive charge. So field due to this gonna be pointing this way at that point. And field due to this one gonna be pointing that way. And distance and charge, they are same, right? Charge is same, distance is same. So that means field, value of the field is same, but they are in opposite direction, okay? So that's why E net is 0. How about potential? Potential is not a vector, it's a scalar quantity. So potential due to this charge is, let's say, kq over r. And so is the potential due to this charge. So that means it's going to be kq over r. Okay. Positive charge means both of these are positive. So it's going to be positive 2kq over r. Okay. They get added. So no zero. So potential is not zero, but field is zero. So it looks like A is correct answer in this case. So they add up, but field being in opposite direction, they cancel. Okay, net becomes zero. Now, potential difference we talked about, and there is a question related to this. And this question is from our example problem in our note. It's already done in the note. So this is basically same picture there. So it talks about 2 points A and B. So this is A, this is B, right? So you are given source charge Q, which is positive 5 microcoulomb, means 5.0 times 10 to the power negative 6 coulomb, fixed at a point, and test charge Q is also positive 2 microcoulomb, was moved towards the source charge in its electric field. Determine the electric potential at point A. So that means it's asking us to find what is U at point A. Okay. So UA, potential, for potential, we don't need this test charge. All we need is source charge. Okay. And where R is given as 0.20 meters. Okay. So basically you plug in, so this is going to be positive potential, right? And then B, it says calculate the potential difference between B and A. So now it says, okay, oh, it is asking us to find both UA and UB over here. So here is going to be RA. Over here is going to be KQ over RB. Okay. So B, here the notation should be B. Okay, I wrote U, looks like U. So I'm kind of being mindful. U means energy, B means potential. Okay, sorry about that. Okay, so that's that. So now change in potential. Oh, why it becomes like a U? So change is final minus initial. So KQ, KQ, they are same, so I can factor them out. You don't have to, but that looks neat. So we need to plug in numbers to get that. And then on the C, it says, okay, find the change in electric potential energy of the test charge. So now, uh, see, for the potential, we don't need that test charge. Only source charge is enough. But for the potential energy, we need test charge. So we need both charges, right? So how do I find that? So what is the change in potential energy? So for that, what you do is you just multiply change in potential by the charge, delta V, okay? So you have delta V and Q is given. So once you multiply, you're gonna have answer. But of course, the numbers are a bit ugly numbers here, okay? This is done in the note. So you wanna do it and then verify if you got it right, okay? If you're not very comfortable working with numbers, sometimes, chance that we may make mistakes. Sometimes 7 minus 2, I may write 4. It may happen, okay? That may happen, although that's not correct. So what are we doing here? When we have charge, charge can have field. Similarly, we can talk in terms of potential rather than field. So this is another way of doing it, okay? And here is a video made by a teacher, looks like very enthusiastic teacher in his school. So this device is called Bandy Graph Generator, okay? So the bottom of that is not visible here. So it has a belt going here. You see, this is plastic belt, and that goes through kind of comb kind of structure. And then there is a motor. So when this, what happens is this, the comb transfers the charge on the belt, and the belt eventually transfers charge to this dome because there is also pointed structure inside here as well, okay? So they are very effective on transferring charge. So they become charged, okay? They become charged. So that means we can say, okay, they produce field around it, or they have potential around that, and so on, okay, when it is charged. So it's like it becomes like a source charge, okay? So now let's watch this video. He's just acting. But there is charge, okay? As long as you are wearing a shoe, that's an insulator shoe, like sole with the insulator, then you're not gonna have, like you won't feel that because you need to feel that you need potential difference. But since you are touching this, your body and this, they are in the same potential, okay? Same thing goes there, okay? Everything here, they are at same potential because they are in conductor, okay? But if you try to touch it, this one has a different potential or maybe even zero potential, okay? Come on, Mr. B, move on. And by the way, link is there. If you like, you can watch it later, okay? So now this one is at a different potential. Now look at here. Basically not that long hair, but you can still notice the hair moving, okay? Because some of the charge jumps here on the hoop, okay? So here is little, they are like Now they are like, let's say, those are, the hair raised, right? But when he brings the finger near there, some of the charge goes there, so they come a bit closer because they are losing some charge. And he brings a pointed conductor, a nail, and that is even more effective than our finger. Our finger is also pointed, but that nail is even more pointed because the area of the tip is very small. Look at the hair now, you can even notice more. Now there is that, see, lightning going on. See that lightning? So that's what happens. Did you notice this lightning over there? So charge jumps from here to there or from there to there, okay? So in that process, charge is jumping through the air. Air, we say, gets ionized. And that's what the lightning strike we see on the air as well. So clouds, when they are moving, they are, there is friction between clouds. So because of that, they becomes charged. So now what happens is there is this big charge is moving, and whenever it finds a way or becomes excessively charged, it leaks some of those charges in the air, and that draws towards the earth. Okay. And if it's on the way, if you are there, then it's going to pass through your body because your body is conductor, especially if you're not wearing, let's say, really thick shoe. But that charge is really strong, very, very large amount of charge. Okay. Even this much thick shoe, it may just pass through that. But if you are, like let's say if there is a tree, sometimes you see this lightning strikes on the tree, tall buildings, and so on, because they are finding the easiest path. So through the body of the tree, they can easily pass rather than the air. Air is insulator. But live tree, it's a bit more conductor because it's moist. Okay. So anyway, so that's how the field and the potential inside and outside a conductor looks like. Inside the conductor, what happens? Field is zero. We already talked about that. Potential is constant, whatever it is, and its value is same as whatever it would be at the surface. So here it has a radius r, okay? So it has radius r. So in this plot, you see the field is zero all the way, but the potential is this much, and its value depends on k, q, and r, okay? But once we go outside, what happens? Then now this whole thing acts like a big source charge, source point charge, and then your potential is kq over r, or I should say little r, uppercase R being this conductor, right? So once you go there, it varies 1 over r, means it decays slowly. But field equation, recall, it has r square. So that means it's going down quickly, because if you double the distance, it is just half, right? If you double the distance, this 1 over r square is quarter. See how quickly it's decreasing. Okay, so field is decreasing quicker. So that's what this graph is showing you. Field is decreasing quicker, decaying quicker than the potential. So this blue line represents the potential, and this line represents the field, this gold line. Okay, so that's what that is. So field inside a conductor is zero, but potential is constant. Okay, outside field goes like 1 over square distance, and potential goes just 1 over distance, not 1 over square, r square, okay, or distance square. So now, looks like we have question exactly related to that. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see, how did we do? Mostly B, and that is correct. So that's what we said, okay, in the previous one. So some of you thought that. So that would be lowercase r. See, the radius, uppercase R is radius. Once it goes outside, that would be lowercase, okay? So if this was like, let's say r square, that would be outside. That would be outside, not inside, okay? The question is, describes the electric at the center of the sphere, okay? So potential is constant everywhere, like equal to the surface, but field inside is 0. Okay, so I said we're going to talk about conservation of energy. So here is conservation of energy, right? Kinetic energy plus potential energy at one point is equal to kinetic energy plus potential energy at another point. Okay, initial, final. So kinetic energy, our good old kinetic energy, half mv square, but potential energy in this case is Q times V, right? Remember, we defined potential as U over Q. So that means energy per unit charge. So that's how we define. So U becomes Q times V, and that's what I'm writing here. So this is electric potential. Okay, so kinetic energy plus electric potential energy. Okay, that's that. So now in this question, it says it is released from point A. Where is point A? Here. What's the potential at that point? Everywhere along that line, potential is 60 volts. So VA is 60 volt. Okay. And at B, past B, where is B? What's the potential at B? Oh, that looks like a 0. Okay, so 0 volt here at B. So that means we know BA, BB, and it is released means initial speed at A is 0, and it's asking for uh, speed at B. Or if you like, maybe you want to write in terms of I and F. That way it's going to be easier. Okay, so that's what it is asking. Mass of proton is known, and charge of proton is also known, which is equal to this 1.6 10 to the power negative 19 coulomb, right? So with these and these on that equation, you can solve for final speed. And in a note, I have done very similar problem. So next class will pick up from the next slide, which is also the use of conservation of energy. Okay, so we're going to be repeating this one more time, but you want to look at the problem solved in the note. Okay. Okay, so looks like I kept you a little longer than 50. Sorry about that. So I'll see you next class. Have a nice weekend and productive weekend.